Hello, so on this particular video we are looking at a past paper problem from an exemplar paper, Gauteng 2020. This is actually 3, not 5. So now this is an electric circuit problem, and if you check this, I'm sure you might have seen this diagram before. So chances are in this paper it came back as it is, or as it was, because it was on another paper before it appeared on this one. So let us check how we would go about solving for this one. On surface level, it looks like a very scary electric circuit diagram, because we've never seen, if you have, but it's quite rare to see a circuit where the conducting wire passes diagonally like this one. It's not something we see every day. But if we follow the principles I've been talking about so far, that the first thing you do is just trace the current, you will find that this thing, it's really not that complicated. It's just a matter of, do you understand your basics? All right, so now what we have here is a circuit diagram where the resistors are connected in parallel. So they are telling us the resistors are connected in parallel as well as in series. Okay, so there's a parallel combination and a series combination. All right, so now the battery has an EMF of 24 volts and no internal resistance. As you can see here, our 24 volts is there. Okay, so since they're saying there's no internal resistance, what that means is, like what I always say, you should just note it here. It means that your small r is 0 ohms, right? So it's not there. So what it also means is, if you remember, EMF is equals to the V lost plus your V external. So V lost is the potential energy that was lost while the battery was overcoming its own internal resistance before it could then supply energy to the circuit, right? So that's how you think about it. So now, since they are telling us that there is no internal resistance, remember, V lost is the total current of the circuit multiplied by the internal resistance of the battery, which is small r, okay? And then V external is now that total energy that will be supplied to the circuit itself. So usually it's lower than the 24 volts of the EMF. But this only happens when the internal resistance is present. In this case, it's absent, so it's not there. So V external is usually given by total current times the total resistance, okay? So if you check our formula, since R is not, it means this component of the EMF is gone. What that means is V external will be there. Let's just return it as V external. So what it means is our EMF is equals to the V external, which in this case it's equals to 24 volts. So you see, I haven't started answering the question, but I'm already interpreting what the statement is saying, so that before I start, I have almost a whole story, right? So that's one of the principles. It's very important. You don't just start answering right away. First off, you must always make sure you check and you deduce basically what the statement is saying. So you build up from it. So now what this means is as well that if we wanted to find I times R, we would say equals to 24 volts. So let's say we have total resistance and we want to find total current. We could use 24 volts, right? And then divide, however, whichever parameter we are given, or whichever physical quantity we are given, we can then find the other one, right? So that's what this means. Now, when switch S1 is closed, the reading on V2, where's V2? is 9 volts when switch S1 is closed. Okay, so we know that V2 is, they said what, 9 volts. All right, so we have that piece of information. That's V2 for us. Okay, so we are pretty much done with interpreting the statement. So now let's check the diagram. Remember, what I always say is start by tracing your current. And if you remember, current, we say it always, well, you imagine it circulating in the conducting wires, right? So it will always start from the longer wire of the cell lines, whatever you want to call them. These lines, they are cells, right? But yeah, it starts moving from this longer one, then it goes that way, right? And then it keeps flowing. So this is still total current, so it keeps going, it goes, this is still total current. So what that means is the 3 ohm resistor will receive total current, right? And then it exits this side, and then it gets here. When it gets here, now there's a branch. There are 2 branches. There's branch 1 and branch 2. Branch 1 has a 2 ohm and a 4 ohm resistor, while branch 2 only has an R ohm resistor. So this resistor, R ohm, well, we don't know what it is in terms of the magnitude of the resistance, but they gave it the letter R. Okay, so it means current now will start splitting. There will be current that will go there. We will call it I1, which means the current flowing in the first branch. And then there will be another current flowing this side because it's dividing now. The total current is dividing into 2. Let's call this one I2, which means the current flowing in the second branch. Okay, so current will flow. Right, so another thing that you must remember, in branch 1 we have 2 resistors, right? These resistors that are in branch 1, they are connected in a series fashion, so in a series combination. So what that means is the current that the 2 ohm resistor will receive will be the same current that the 4 ohm resistor receives. So this I1 that comes into branch 1 will be the same throughout until it exits this whole branch. Okay, so now I2 will be the one received by this R ohm resistor, and then we go about it. It goes there, still I2, right? Goes I2 all the way there until this point. Okay, so when it gets there, they add up again and they form the total current, and then the current recirculates. So it becomes I total again. So I total in this example, we are using the letter I, which represents total current, and I1 represents current flowing in the first branch, I2 current flowing in the second branch. So what we can do is we can change the color here so that you can see the different currents. Let's make I1 purple and I2, let's make it red, okay, or blue, so that you can sort of see how it flows. All right, so that's what we have here. I1, I2, when they get here, they add up to make our total current again. Okay. All right, so before we even start defining, let me just show you what this circuit actually looks like. So in simple, this circuit looks like this. In a configuration that we used to, at least it would look something like this. You'd have the cell there, I mean the battery or power source, and then now energy source. You have, let's see, a switch, so let's do this. you have that, and then okay, and then the other one, so something like that. Okay, so you would have our wire. I won't draw everything, but I'm just drawing the arrangement of I'm sketching the arrangement of the resistors, right? This is essentially what we have in this problem. After tracing the current, we can see that in actual fact we have something like this. So it's just that whoever created this diagram was trying to test if you get the logic behind this circuit. So now this is basically it. You would have the 2 ohm here, the 4 ohm, and then you'd have that R ohm, and then you have the other resistor there, which is 3 ohm. You'd have it there, and then your switch S. Right, so this is basically the circuit we have. Right, this is something we used to. There's this configuration. It's something that's familiar to us. So that's one thing. So now going to potential difference. Let's go there, 8.1. Potential difference is essentially, or how we define it is, it's the energy transferred, right, per unit electric charge flowing through a conductor or across a conductor. So, but what does it mean? So what it usually means is, let's say you have a conductor, right? And then this is your conductor. This is point A and point B of the conductor. So energy flows like that from A to B, for instance, right? And then what we're trying to check is what is the difference in energy between points A and B, right? So usually we check this because there's a resistor somewhere there. So we check this potential difference because there's a resistor somewhere there. So even the word potential difference itself, right, it's explaining, because we are taking the difference between the energies in point A and B, right? So that's why if you check your voltmeter, it's always connected between 2 points. You find it connected like this between points before and after the resistors. Call this our resistor R. What it's essentially doing is it wants to see the difference in energy between points A and B. Remember, when charges are moving in a circuit, they carry energy, right? So that energy is what you normally call voltage. So potential difference is essentially voltage. It's given by this formula. So when we say potential difference across the ends of a conductor, which these ends in my example are A and B, and we say, well, that potential difference across those ends of the conductor is the energy transferred or work done per unit electric charge flowing through it. So we are basically saying that for every charge that's flowing across the ends A to B, right, it carries an amount of energy. It carries a certain amount of energy, right? And then we want to see that as it moved from A to B, how did that energy change, right? So that's what we call potential difference. So that's what we call voltage in everyday physics terms, right? So that's how we define potential difference. It's just the difference between these 2 points, A and B. We want to check how the energy is changing. Is it dropping or is it rising, right? Because remember, for charges to keep carrying energy across the resistor R, they will have to overcome that resistance there, right? There's a certain amount of energy that will be used to make sure that charges flow across the resistor R, right? So in resistor R, there's a number of things that could be happening. It could be a bulb, it could be a heating element, it could be anything really. So in resistor R, what will happen is that energy that the charges are carrying will be used, some of it either to produce heat, or it will be converted to heat energy if this resistor R is a heating element, or light and heat energy if this thing is a light bulb, or whatever other energy form, right, that this thing can be converted to. So that's why we need to understand that how is this energy changing between points A and B. So that's basically what it means. Okay, so yes, that's voltage in a nutshell, potential difference. So let's write our definition. So that's it. Potential energy across the ends of a conductor is the energy transferred or work done per unit electric charge flowing through it, given by the formula V is WQ. So this Q represents your charge, and this W represents the work done by the charge to transfer the work done, or the energy transferred, and usually it's in joules, right? Charge is in coulombs, and then that's how we define potential difference, not energy. Okay, so yes, now let's continue to our next question, 8.2.1. The current through the 3 ohm resistor. So when we were tracing the current, what we noticed is that the 3 ohm resistor will receive our total current. So what that means is, if I know how much voltage flows through that 3 ohm resistor, I can find my current flowing through the 3 ohm resistor by saying R is equals to V over I. So currently I only know the resistance, but I do not know how much voltage is flowing through that 3 ohm resistor. All right, so if you check our circuit here, our circuit there, it has a voltmeter like this, and we are told that this voltmeter measures 9 volts. Okay, and then here our EMF is exactly 24 volts. Let's see, just to make sure. All right, so what that means is we are left with about 24 minus 9, which is 15 volts. Okay, so where is the other 15 volts going to? That other 15 volts is going to our 3 ohm resistor, right? How do we know? Okay, so if this voltmeter is measuring 9 volts, it means the parallel combination is receiving 9 volts, the entire parallel combination. Why? Because remember, in a parallel circuit, voltage remains the same, so there won't be anything such as V1 or V2. Even if there was, it would mean that V1 is the same as V2, and that is 9 volts. That's what we are saying. So the voltage flowing across the first branch and the voltage flowing across the second branch, or the potential difference in the first branch and the potential difference in the second branch, is practically the same, which is 9 volts, right? So that's what we are saying. So it's basically V is equal to V1, V2, which is equal to 9 volts. And then the only thing that differs, which the rule says current divides in a parallel combination, is the current, right? So I1 and I2 will not be the same for a parallel combination, but they will be the same for a series combination. Okay, so now we know that the 3 ohm resistor receives 15 volts, but obviously we have to show all of our workings. So let's do it. We will say voltage is equal to 24 minus 9, which gives us 15 volts, right? Then from there we can say R is equal to V over I. In fact, since we're looking for current, we could have said I is equal to V over R, but it's fine. Then you can substitute 3, 15, and I. Therefore, our I is simply equals to 5 amps. So this is our total current. It's not only just current flowing through the ohms, this is also the total current flowing in the circuit. We are keeping note of that. Right, so now that we know our answer to 8.2.1, we can go to 8.2.2. All right, so 8.2.2, the current through the 4 and 2 ohm resistor. So they want what? We are told to find I1, because I1 is the current that will flow through the 2 and 4 ohm resistors. Right, so let's see if we can find that. We already know the voltage flowing through these 2 resistors. So it's as simply as also using Ohm's law here to find the current I1. So we can still say, we are told to find what the current is. We can still say I right? The voltage is 9. The resistance, we'd have to use the total resistance because these are connected in series, okay? So the total resistance is 2 plus 4. Which is 9 over 6. And then you can get your answer. And that is 1.5 amps. Okay, so this is how much current flows through the 4 and 2 ohm resistor. Basically, this is the amount of current that flows in the first branch. Okay, so the first branch is in a series connection, so you can't say I1 is equals to 2 over V over R, right? But then now when you substitute for R, you use the 2 ohm or the 4 ohm only. It's not physically true, because what you would be saying in that case is the total resistance of that combination is 2 ohms, which is not the case. The total resistance of the series combination in the first branch is actually 6 ohms. Okay, so you would have to use the total resistance, unless if there was only one resistor there, then you would use that resistance because it's the total resistance, right? So unless if maybe only the 2 or the 4 ohm resistor was there, not both, then you could say, okay, my R is 2 or my R is 4, and then you use the voltage being 9 in this case, and then you'd find your I1. But if there are 2, 3, 4 or more resistors, you have to add all of them up, and that represents the resistance of that series connection. Okay, then you can find the current flowing through that series connection. Okay, now let's go to 8.2.3. The resistance on R. All right, so there's a number of ways in which you can do this one. So we already know what our I total is. We said it's 5 amps, and then our I1 is, which is the current flowing in the first branch, is 1.5 amps. And then we know that the total current is basically a sum of these two currents, I1 and I2, right? So we can find the current flowing through branch 2, which is where the R ohm resistor is located. So we can say, if you want, 5 is 1.5 plus I2. Then you can say I2 is 5 minus 1.5, which is 3.5 amps. Okay, so then you know that's your current in the R ohm resistor. Then from there you use Ohm's law again. So I'm sure what you should have noticed by now that this question was so straightforward. But if you failed to notice that this was just a simple circuit and the only thing that would have scared you was going to be this diagonal branch, which is something you not used to, but following the principles of tracing the current and so on, you would know that this is just a basic circuit. So everything that followed after was just straightforward. So what we're saying now is the current here, I, is simply 5 minus 1.5, which is 3.5 amps. That's the current that will flow in that R ohm resistor, 3.5 amps. Okay, so now from here you can say, well, my resistance then is V over I. And then let me try to squeeze everything here. My voltage flowing through that R ohm is 9, and the current now is 3.5. Therefore my answer is 2.57 ohms. So that's the resistance of resistor R. All right, so let's move to 8.3. The 4 ohm resistor burns out. Where is that? Okay. What will happen to the current in the circuits? Right, only increases, decreases, or remain the same. Okay. And then explain your answer. So these types of questions, they require your knowledge of Ohm's law. So we know that in Ohm's law, if we check this formula, if I come and increase the okay, let me use this one for instance. Okay, if I come and I increase the resistance, my current will drop. Why? Because remember, mathematically, if I have 5, let's say I keep voltage, the voltage supply the same, I don't change it, but then I change my resistance, starting with 5 over 2. Let's say my resistance is initially 2. I will get a current of 2.5, right, amps. Now I increase the resistance, I make it 5. I will then get 1 amps. So do you see that by increasing my resistance from 2 to 5 ohms, I have reduced my current from 2.5 amps to 1 amp. So that's usually what happens. So you need to have that basic knowledge of Ohm's law, right? So usually we're keeping one thing constant and we're changing the other. So now in this scenario, what happened when I burn my 4 ohm resistor? And then you bring it to Ohm's law, and then that's how you answer it. So in this case, if you check, if I burn this 4 ohm resistor, what will essentially happen is there will be no current flowing past the 4 ohm resistor anymore. So what will happen as well is where there was the 4 ohm resistor, what will happen, you'll have think of it like an open switch. There'll be a gap there, so current won't be able to flow through this branch anymore. It won't be able to flow through the first branch because now there's been a gap that has been opened there since the 4 ohm resistor is no longer working. So once you bend that 4 ohm resistor, it's like removing it and not replacing it with a conducting wire to close that gap in a sense, right? So it's like you've created an open switch where there was that conductor. So what does that mean for our circuit now? Now that there's a gap there, no current will flow in the first branch. So our circuit then becomes such that current will only flow in the remaining resistor. So you'll end up having something like this. Actually, let's go and throw it 8.3. What will happen is you'll end up having something like this. Okay, this is unnecessarily long, but you get the point. Right, you'll end up having something like that. So that diagonal or that other branch is gone now. Could have actually used this circuit. This whole line is removed now. That whole branch. So what you are left with now is just 2 resistors, which is the 3 ohm resistor and the 2.57 ohm resistor, the R ohm resistor. Okay, so it means also now it changes the nature of your circuits. The circuit now is mainly a series circuit. Okay, there's no longer a parallel combination within this circuit. So what does that do for your resistance then? If we try and compute our previous resistance, let's see what it was when this thing before it burned, right? We would have R is equals to RS plus RP, where RS represents my series connection and RP represents the parallel the equivalent resistance in the parallel connection. So RS, we would only have the 3 ohm there, and then RP, we would have, you would calculate it by saying 1/6 plus 1/2.57, right? Remember, you can't say, if you're calculating the RP, which is the equivalent resistance for the parallel combination, or the total resistance for the parallel combination, you can't say 1/2 plus 1/4 plus 1/R, okay, which this R, we just calculated it to be 2.57, okay. This is wrong. You can't do this one. The reason for that is, think of it like this. We are saying that, of course, this is not exactly how it is, but think of it like that. We are saying that we have matching resistors like this, right? So we have 1 on the other branch and 2 corresponding to that one. They are in parallel, or 3 on the first branch and 4. So if you have equal resistors like this, in the first branch there's 2, and then in the second branch there are also 2 resistors. You could have done that. Let's call this one maybe R2, that one R3. You could have said, well, 1/2 plus 1/R2, right, plus 1/4 plus 1/R3. Then all of this you invert it, right? So this is allowed. But now that there's no pair, right, in this case there is no pair, they are not paired. There are more resistors in the first branch than there are in the second branch. So you must first add up the ones that are in the first branch such that they make up one big resistor called the 6 ohm resistor. And then now in the second branch you'll have the R ohm resistor. So these two are now in parallel, right? So then you can use our formula 1 over 6 and 1 over 2.57, because that's a pair, right? So you want it to be in pairs, otherwise don't just don't just add. It's not correct. Okay, so that's one thing I want you to understand. Okay, think of it like that. They must be in pairs. If there are more resistors in the other branch than there are in the corresponding branches, then you don't just put them in the formula. It's not good. All right, so that's what we have, and then what this would have given us is 3 plus 1 over 6 this is 1 point, I get 1.8, right? So we would have gotten 3, sorry, let's change this. We would have gotten 4.8 ohms. Okay, so this is our resistance, total resistance, before the 4 ohm resistor burned. But once we burn the 4 ohm resistor, now our new resistance will be R is simply R1 plus R2. Why? Because now it's just a series connection, which would be 3 plus 2.57, and this is 5.57. So do you see that our total resistance has increased from 4.8 ohms to now 5.57 ohms? Okay, so we can take this. Let me take this. Let's take this that side. This is our before after picture. So we are saying before 4 ohm burnt out, right, we had this total resistance. Now after the 4 ohm resistor burnt out, we have our new resistance being this one, right? Now we can start crafting our argument or our reason. Therefore, what question was it? 8.3. So what will happen to the current in the circuit? Choose only increase, decrease, or remain the same, and then explain the answer. Okay, that's good. So 8.3. We know that current is equal to the voltage divided by R. So we are saying we are keeping the battery the same, but we just burn out the 4 ohm resistor, right? So what happens if we burn out the 4 ohm resistor? We notice that the circuit gets rearranged. The new circuit becomes primarily series connection only. So, and then what happens as a result is that our total resistance for the circuit increases from 4.8 to 5.57 ohms. Okay, so we know that increasing the resistance while of course keeping the total voltage supply the same will reduce our current, right? So that's what will happen. So we can say that our current will decrease, or they said decreases. Why? After the 4 ohm resistor burns out, the total resistance of the circuit increases. That's the first thing we say. And according to Ohm's law, the current is inversely proportional to the resistance, and therefore the current will decrease. That's what we're saying. Okay, so let me write it for you. All right, so this is what it is. So when the 4 ohm resistor burns, the total resistance of the circuit increases, and then since the current is inversely proportional to resistance, this thing, then therefore the current in the circuit will decrease. That's it. Right, so that's how you would explain it. So this is how you would handle questions like 8.3. You must just understand in Ohm's law how each physical quantity affects the other one. Right, so yes, that's it for this video. I will catch you on the next one.